we've got 3 of the golden equations, and we need to derive the 4th. And the question is, what if we don't have time? What if we don't have, oh, okay, never mind. If we're working and we do not know how long some motion takes, then we have to have a way to get there without having measured time, perhaps, or not having time available to us. So we're going to start off using 2 of the golden equations that we've already got. We're going to start off actually with our first one, delta x equals 1/2 vi plus vf delta t. And then we get rid of the fraction, so I'm going to multiply everything on both sides by 2. And I'm just going to show that like this. And remember, it's legal to do anything to one side of an equation as long as you do it to the other. So that gets us this slightly more reasonable looking, no fractions anyway, equation. And I'm going to solve this for delta t. Because very often when we're working towards using an equation and we don't have a variable, we actually want to try to solve something else for that variable so that we can do a substitution. So here we can create an expression for delta t that doesn't require us to have measured delta t. So I'm going to get 2 delta x over vi plus vf equals delta t. Okay, good. I have an expression for delta t. Well, you know, in any of these problems, I have to have something to work with. So I'm going to start with another of the equations that we've used, which is vf equals vi plus a delta t. Well, right there, I've got a place that I could plug this into. And what that's going to give me is vf equals vi plus a times 2 delta x over vi plus vf. So this is going to give us a way to use our displacement, our rate of acceleration, and our initial and final velocities. So now I want to do a little bit of simplification, a little bit of algebraic magic. Vf equals vi plus, well, my first step would be to distribute the a times 2 delta x over vi plus vf. Well, I want to get the fractional portion here isolated so that I can make this into a multiplication division problem. So vf minus vi equals a times 2, whoops. This is usually, and I'm reverting, it's usually written as 2a delta x over vi plus vf. Who was it who said they loved FOIL and they just lived for doing FOIL problems? And they woke up in the morning thinking about foiling polynomials? No? No one? No. I must have imagined that. Well, you can probably see that at this point what we're going to end up with is something that we could FOIL. What does that give us? Do you remember this one? Do you know this one off the top of your head? Vf squared. Go ahead, louder. Vf squared minus vi squared. And I actually usually have to prove that to myself by foiling the darn thing, but I'm going to trust you because I can never remember if it's plus or minus when you get done with it all, so I have to like do it once and then I'm okay. We'll just trust Sadie. She seems sincere in her belief. So that's equal to 2a delta x. Because this equation is most commonly used to find displacement, it very often gets written as, very often used to find final velocity. This most often gets written as vf squared equals 2a delta x plus vi squared, or vf squared equals vi squared plus 2a delta x. Yeah, that's the one. I knew one of those would sound, oops, squared. So that's our last golden equation, and that gets us our full note card. And so at this point, your full note card should have all of this on it. So you may want to check yourself. Your basic equations for average velocity and acceleration plus your 4 Goldens. In the old building, the last couple years when nobody cared what happened and I could just give kids poster paint and tell them to paint things on the walls, we had a lot of fun those last few years. I wanted them to make this golden scroll that like had light shining out of it that would have the 4 golden equations on it. They didn't quite capture it, they just did it in Sharpie. But these are really useful and we will use them and abuse them. So with that, let's do the, what are we on? 2E, last of the little sections. We've got the plane. We're given the acceleration of 4.8 meters per second squared. We're given a delta t. I thought the whole point here was to do this without delta t. Oh, well, no wonder. I was like, why are we getting time? We want things without time. Let me scratch that. Pushing a stroller starts from rest, uniformly accelerates at 0.500 meters per second squared. What's the velocity of the stroller after it's gone 4.75 meters? So what have we? Well, we have VI. We would like VF. We have the rate of acceleration, and we have a displacement. VI equals 0. VF, wouldn't you like to know? 0.500 meters per second squared, delta x being 4.75 meters. Of course, this is a great time to use our shiny new problem. VF squared equals VI squared plus 2a delta x. And to solve for VF squared, we only have to do one thing. Take the square root of both sides. That's a really common place to trip up, to forget to take the square root. And I honestly don't know how to tell you to not make that mistake because that's one that I haven't managed to talk myself out of, and that's my most common mistake. I know that it is, so I tend to check myself on that, but I'll forget to take the square root. So we're going to plug in VF equals the square root of, 0 squared, well I like that, times, or plus. Hey, let's do a little bit of dimensional analysis here, shall we? Meters per second squared times meters gives us meters squared over seconds squared, and we're going to take the square root of the whole darn thing, so that's going to give us meters per second. That seems about right for a velocity. What do we get for a raw answer? Okay, so we get the 2.17, etc. It is going to sig fig out to 2.18. Do we have 3 sig figs? Yes. So it's going to sig fig to 2.18 meters per second. Okay, you've got all the 2E problems assigned. If you're still working on 2C and 2D, I would advise that you at least dip into these today, do the book problems. That's it. You got time.